in our process we need to try to recover our copper, what we're going to do is reduce it out of solution. And the way that I'm going to do that is using aluminum. You can see some bubbles forming on the surface, and you can see a little bit of discoloration, but the particular reaction that I'm interested in, right, which is the aluminum transferring electrons to the copper and reducing copper out of solution, doesn't seem to be happening very quickly. And that's kind of strange, because based upon what we know about single replacement reactions, you would expect this particular reaction to go pretty quickly. One of the things about all chemical reactions that we know is that they need to have both of their reacting components touch each other on a molecular level at each stage in order for the reaction to progress at any rate. And in a single replacement reaction, one of the two reactants is a solid. Aluminum itself is exceptionally reactive, but the problem is that it's coated with this extremely unreactive aluminum oxide surface. Even in the presence of an acidic solution, one of the things that's a problem is that the acid will react with the aluminum oxide surface if it's sufficiently strong, and that'll generate hydrogen gas, and the aluminum ions will move into solution. But the aluminum binds water, and within a very short period of time, only like a few molecular distances, usually the aluminum with the water stuck to it will precipitate out again as aluminum hydroxide. And so you actually get kind of like a jelly coating on the outer surface of the aluminum that isn't more accessible than the aluminum would have been with the aluminum oxide to begin with. So you have this really, really reactive aluminum metal, but it has this really, really unreactive aluminum oxide outer surface that's keeping it from reacting. You add acid to it, of any kind, and maybe you get some bubbles forming, but immediately after that, the aluminum ions will precipitate out with the water to form aluminum hydroxide kind of as a gel on the surface, and then the reaction stops again. So one of the only ways to get these reactions to work is actually to use hydrochloric acid. In this case, the generation of the hydrogen from the hydrochloric acid is not productive, right? You're consuming aluminum, and the aluminum is going to be reducing hydrogen, not the copper that we're interested in. And the chloride ions that are going to be in the solution, that are sort of going to be sticking to the aluminum a little bit as the aluminum wanders away from the surface, from a first order sort of approximation, the way that we would write chemical reactions, they're spectator ions / completely irrelevant. However, it is just the case that sometimes when you look at reactions like this, if you ask yourself the question, why is it that certain procedures call for one kind of acid and certain procedures call for another? The reason is that there can be these very, very specific issues, and a lot of it, in this case, for example, has to do with surface chemistry. It has to do with the fact that if we were just asking the question, does the aluminum in that wire want to react with the copper that's in the solution, the answer to the question would be absolutely, right? That's favorable from a chemical perspective. But from a kinetic perspective, in terms of getting the two components to mix together, it's just has a tendency not to work. So what we have to do is we have to add hydrochloric acid to this system, and the hydrogen that's generated on the surface serves to sweep the surface clear of ions. Those bubbles will sort of clean the aluminum and blow the aluminum ions that are trying to precipitate out away. And in addition to that, the chloride ions that are part of the hydrochloric acid will transiently stick to the aluminum ions and serve as a sort of ligand that will shepherd the aluminum into solution to somewhere where it's not going to cause us a problem. So again, this is 6 molar hydrochloric acid. It's going to make our solution pretty acidic. Now, one of the things that you might also see is that there's a slight color change, and that's also because as we add a little bit more acid, what's going to happen is that we're going to protonate both of the sites on glycine that would stick to the copper, and that means that the glycine's not going to be an effective ligand anymore. So you're going to see less of the violet color of the copper glycinate complex and more of the blue color that would come from a copper solution all by itself. And that's what you can see, for instance, at the very top here, as these things start to mix together. The glycine is still going to serve as a great internal indicator, because what happens is that over the course of this chemical reaction, all that excess acid that I added, that's going to end up reacting with the aluminum surface. So I got the acidity very high by adding that couple of pipettes full of acid. And now that extremely acidic solution is going to be reacting with the aluminum wire. So some of the acid is going to be reacting, is going to get reduced to hydrogen gas. And then that process of clearing off the aluminum surface, right, and revealing fresh aluminum metal gives the copper an opportunity to react with the aluminum metal and to precipitate out. I have a pre-weighed vial that I'm going to transfer my product into. So in this case, I'm just doing a delicate rinse, and usually, if this is a reasonably tight spiral, then you can get all or most of it into your container. Now I'll add a little bit of water and shake my piece of wire around in there. Now at this point, I do have a decent amount of solid that's stuck to the aluminum. And so what I'm going to do is use a spatula to, as near as I can, scrape this material off and into the flask. I don't want to do this too vigorously, obviously, because I don't want to knock aluminum filings into my product. So it's a little bit touchy. And my hope is that after scratching that surface a little bit, when I run water down it, that it'll carry particles in there. But there's always going to be a little bit of product lost, right? So I definitely do see that there is some copper that's still precipitated out on the aluminum wire. And I could think about either going after that or trying to determine its mass, but there's going to be a lot of confounding issues, right? If I try to weigh the aluminum wire before and after, then some of the aluminum consumed is going to be a result of the oxidation with the copper, and some of it's going to be the oxidation by the acid, and I'm not going to be able to know how much of the aluminum was oxidized by the acid. I have no expectation of what the ideal mass of the aluminum wire should be at the end. So if there's a little bit of copper that's left over on it, unless I somehow sort of remove it kind of by polishing it. But then if I do that, the question is, have I removed copper or have I removed copper and aluminum? It's, it's not really very easy to figure out how I'm going to recover and or quantify the amount of copper that's left on there, which is one of the reasons in this particular procedure. As with any procedure, when you're trying to recover something, sometimes that there's material that you don't have, and you just sort of have to shrug and say, yeah, that's the source of error. That's where our potential quantitative loss is coming from. Actually, it's not potential; it's certain that loss is coming from there. So here's my product, and I'm going to just take the water off of the top of it using a pipette. And then I'll add some water to it again. So now if I'm going to weigh it, I got to get rid of the water. And a standard way to do that is to add a drying agent. In this case, what we're going to do is we're going to add some methanol. And so the idea here is that methanol and water are completely miscible. So the methanol will dissolve the water, break up its surface tension, and help it be more volatile. And then I'll use my pipette to get rid of the methanol. Now, this particular lab at this particular moment in time is pretty humid, and so just using methanol to dry out the water is going to be kind of a challenge. So I'm going to do this in a couple of stages. So one stage is adding the methanol to get rid of the water, and then the next stage is adding ethyl acetate, which is another organic compound. And the idea behind the ethyl acetate is that methanol is completely soluble in ethyl acetate, and ethyl acetate also contains hydrogen bond donors, hydrogen bond acceptors, no hydrogen bond donors. But it contains enough hydrogen bond acceptors that if you have a solution that's got methanol and it's got some water in it, that the ethyl acetate will dissolve all of the methanol, and it'll also take away the water as well, all in one homogeneous phase. And so we're using the methanol to get rid of the water, and then we're using the ethyl acetate to get rid of the methanol, and then finally we're adding some cyclohexane. Now, cyclohexane doesn't have any hydrogen bond donors or acceptors and isn't soluble in water, and you can definitely see how it's forming kind of a weird separation there. But the point is that adding the cyclohexane gets rid of, because ethyl acetate and methanol are both completely miscible with cyclohexane, the cyclohexane will get rid of those two solvents that we just added. So the hope is that we end up with something which is our product that's wet, but is now covered mostly with sort of a mixture of organic solvents as opposed to water. Now this can go away because it's all done. And in this case, what I'm doing is I'm just putting an oversized cap on top for a second. And now I'm going to turn the hot plate on. So a dilemma that we have is that we've generated our product, we've generated our copper as a relatively finely divided powder. And so it has a lot of exposed surface area that could potentially oxidize, which would make it hard to weigh quantitatively. And so then the question is, well, so how do we get it dry so that we can weigh it and at the same time not oxidize it, right, and change it to some other substance. The answer to that question, or the hope, is that we keep that oversized cap on top of there, and also we rely on the fact that as this organic solvent, that lasts like half a milliliter or whatever, is boiling away, that it's refluxing, right? So it boils, and then it sort of, the vapor is constantly rolling back down and recollecting inside of this container. As that reflux forms, what that has a tendency to do is it's going to fill up this entire vial with solvent vapor as opposed to air, right? So if this was formerly filled with air, at the moment that you start to see this reflux form here, that now this is entirely filled with some combination of methanol and ethyl acetate and cyclohexane vapor. So that half a milliliter of ethanol, of methanol and cyclohexane and ethyl acetate has all vaporized, and it's filled up that container, and our thing is now hot enough, right? And so we're sort of at this delicate balance where what we want to do is get rid of these vapors that are in there, which requires us to sit this on a really hot surface for a second. But we're relying on the fact that for at least a moment, this doesn't have anything in it except for solvent vapor. And that's going to protect our metal from oxygen.